All right, so we're looking at section 2.5, the chain rule today, and let me first talk about what the chain rule says. The chain rule is in particular for the purpose of having when we have one function inside of another one. Okay, anytime you have a function with x and some other stuff embedded inside of a bigger function, and there's several ways that can look. The chain rule tells us how to take a derivative of a function like that. So what you see right here is you have the derivative of the function f. And then you see g of x written exactly like g of x was written here. No changes made at all on the inside. And then you see the derivative of the g function, so g prime of x. You'll hear me use the phrase, and you'll see, okay, let me try one more time. And you will see this described as well as something like this. Taking the derivative of the outside times the derivative of the inside. So you'll hear me reference that language quite a bit. Okay, so we're going to do an example. As we're doing this example, it's very helpful when looking at this to start with to identify what's inside of something else. So what does it look like is inside of something else here?
6 minus x squared is inside.
The power of 5, right? Yeah. Okay, so this part that I've drawn in sort of this red box, that's the something that's inside of something else. Okay, so if you can sort of block out that in your mind, it's big old red box. That's what it is. It's not 6x minus, or 6 minus x squared. It's big old red box right now, or whatever, okay? What we're looking at then for the beginning of this is we're looking at the outside stuff, that power of 5 and that coefficient of 2. So only thinking about the power of 5, the coefficient of 2, if I have a power of 5, what do I do when I take the derivative?
Bring it down and multiply it by 2.
Right, I bring it down and I multiply it by the 2, so I have a 10, right? And then, I'm just going to leave the parentheses here by themselves. What do I do about the power of 5? Yeah, I subtract 1 from it, and I get a 4. So this right here is the derivative of the outside. This is the f prime part. And then what does it say over here is supposed to go inside that set of parentheses then? The original function that was already inside. So whatever was inside that red box, in my case it was 6 minus x squared, will stay 6 minus x squared. We don't mess with it at all, okay? That's the derivative of the outside. Then we multiply this by the derivative of the inside. That means the derivative of the 6 minus x squared. So what is the derivative of the 6 minus x squared? Negative 2x, exactly. So this is where you would stop on the quiz on Monday, right? You would stop right here. Dean's already smiling, interested, and saying, yeah. All right. We're going to simplify a little bit. We're not going to FOIL this out to a power of 4 or anything like that. But what we're going to do is we are going to combine the 2 and the negative 2x and the 10. So as our final answer for this, it's actually going to say negative 20x and then 6 minus x squared to the 4th. Okay? And you just did your first chain rule. Okay? Or at least you did in this class, your first chain rule. Some of you have done this before, I know. Any questions on that one before we try another one? Okay, let's go with another one then. Now this one doesn't quite look like it has something inside of something else. In fact, you might be looking at this and saying, well, that looks like a quotient rule. And you could use the quotient rule to do this. And if you were on a quiz and you weren't being told to use the chain rule specifically or something like that. It's not a very natural approach to use the quotient rule, though, and the reason it's not is because I don't really have a function of x on top. I just have a constant. So it's a little bit awkward to use the quotient rule, and that still works. It's just a little bit awkward. The chain rule is a little bit more of a natural approach, even though the beginning part of it feels a little bit awkward. So what we're going to do in the first part is we're going to write that denominator with an exponent of what would you think?
-1.
-1. You're allowed to do that, right? You can take what's in the denominator and bring it up to the numerator by making it a -1 exponent. Now, you can't sort of make each of the individual exponents negative. It's the whole thing that's in the denominator, so the whole thing has an exponent of -1. Once it's in this form, it looks like a chain rule, doesn't it? In fact, it looks a lot like the last one. We've got something inside of a parentheses, and we've got an exponent that's the outside part of it. So this part of it actually looks quite a bit like the last one. So starting with the derivative now, we rewrote one step to help us with the derivative. What's the outside function doing? Or what is the outside function? It's that -1 power part, right? It's the something raised to a power of -1. So how do I take a derivative of something, in this case, everything in my parentheses, with a -1 exponent? Bring the -1 down, and what will the new exponent be? To the -2. Okay, so this is the outside part of the derivative. And then what goes inside the parentheses? The original thing that was already inside the parentheses. None of that changes. So this is x squared plus 3x minus 1. Am I done? Not quite. What am I missing? Yeah, the derivative of the inside. So what is the derivative of this inside function? 2x plus 3. Very good. Again, on Monday, we'll just stop right there. But as you're working with your homework and simplifying, we are going to change this a little bit. In particular, this part with the exponent of -2, that part can go back down into the denominator with a power of 2, right? And as you take a look at that, you might think, well, think about the, let me write this first. You think about the quotient rule. The quotient rule has the denominator squared in the denominator. And look, that's my original denominator squared, isn't it? So it's definitely pulling back that idea. The other thing that I have then is I have this -1 out here, and I have the 2x plus 3. So in my numerator, I can have -2x minus 3. Okay, so that one was a little awkward to start with, but the solving of it was quite the same as the last one, right? A little bit different simplification at the end, but the derivative part of it was very similar. Okay, let's try another one. This one is actually a little different for several reasons. So tell me some of the things that make this one different. It's underneath the square root. We haven't done that yet. So let's actually change it so that the square root isn't sort of different than the last ones we've done. What would we have to do? Okay, so one way to handle this is to write 3t squared minus 2 over 2t plus 3 and raise it to a power of 1/2. So now it looks a little bit more like what we had before. There's something else that makes this different. Yeah, I've got a quotient inside of the thing that's inside is itself a quotient, isn't it? So what's that going to mean for us as we do this problem? We need the quotient rule on the inside, and we need the chain rule as we're dealing with the outside part, don't we? So this problem gets a lot messier because we're using two of these more complicated rules at the same time. Now, there is one other way that we could do the problem. I just want to mention it. The way that we've got it set up is what we're going to do because it's probably the most straightforward. Sometimes I'll have students who will write it like this. If you write it like that, it's a quotient rule on the outside, right? You're doing a quotient rule, but then when you take the individual derivative of the numerator and the denominator, you're doing a chain rule. So you actually have to do two chain rules if you do it that way, okay? They both yield the same answer if they're all the way simplified. I mean, they are the same thing. So either of those options will work. We're going to do the first one because I think it's a little bit more straightforward. All right, so we're going to do h prime of t. And we're going to deal with the chain rule part first. So, what's that mean I'm going to do? Pull the 1/2 down. Good. Then what will be my new exponent? -1/2. Good. What will go inside of the parentheses? The original thing that was already inside the parentheses, right? So 3t squared minus 2 over 2t plus 3. So in some sense, you could say you're half done, except that I think you've done the easy half, right? The other half's the part that's a little bit longer. However, I do have polynomials on top and bottom, so they aren't terribly ugly or anything. All right, so quotient rule. We haven't done that in a couple days together. So as the quotient rule stands, what do I do first? All right, write the denominator as is. So that's 2t plus 3. Sorry. There we go. And then what? Derivative of the numerator, and that's 6t. Perfect. What comes next? Minus? Okay, minus the derivative of the denominator. Christian wants to do, that's 2. Times?
3t squared minus
Perfect. 3t squared minus 2. What will this all be divided by? Right. 2t plus 3 quantity squared. And you'll be very pleased on Monday when you stop right there, right? Because we're not stopping there today. We're going to simplify that, and that looks really messy right now so far, doesn't it? All right, but I promise you'll be okay. We can do it. Okay, so let's take a few steps to simplify that. Let's see. Let me rewrite my 1/2 for the moment. And what can I do to make that negative 1/2 become a positive 1/2? Okay, but I don't want to take like a complicated fraction into the denominator of a fraction. Flip it. Edgar's saying flip it, right? So whatever's in the denominator can be in the numerator, and whatever's in the numerator can be a denominator. It's part of an exponential property. So I'm allowed to do 2t plus 3. And while I do this, actually let me do one other thing at the same time because we're going to do it at some point anyway. I'm going to go ahead and write that individually to the power 1/2. And then I've got the 3t squared minus 2 to the power 1/2. So I did two things at the same time there. I flipped the fraction, and I identified that the power can go on each of the numerator and denominator separately. Is everybody good with that step? If you need to see it in 2 steps, of course, you could do it that way. Numerator, I want to clean up this numerator because that's a mess. So the denominator right now is still going to be that 2t plus 3 to the power of 2. What about that numerator? Well, we're going to have to distribute, right? So as I distribute, what do I get? 12t squared plus 18t. Good. And then over here, somebody said minus. I agree. Minus 6t squared plus 4. And 2 of those pieces combine, correct? So these two right here will combine. All right, so the first part stays the same. I have the 1/2 and then my numerator over here changes to say 6t squared plus 18t plus 4 over, whoops, 2t plus 3 squared. All right, so help me out. There's at least a couple more things I can simplify with the current expression.
short, cut the 2t plus 3 squared.
Okay, so this one and this one, is that what you're recognizing? Yeah, I've got a 2t plus 3 in the numerator, and I've got a 2t plus 3 in the denominator, right? So I can combine those. How do I do that? What does that leave me with when I combine them? I mean, it's going to be a 2t plus 3, but how many of them?
Minus 1/2 without them.
Okay, so, but then I have a negative exponent, don't I?
That's going down, so
Okay, so I have 1/2 of these on top, right? And I have 2 of them on bottom. So one way to think about that is to think about properties of exponents where we can actually subtract. If we moved, in other words, this down to the bottom, it would have a negative 1/2 exponent, right? And that negative 1/2 exponent plus this 2 exponent could be combined. Negative 1/2 and positive 2 would be what? 3/2. So I can have that same expression with a power of 3/2, but it'll be in the denominator that way. Okay? Some of you are looking at me like you're not quite so sure. These are just properties of exponents, which is something from college algebra, so it might have been a little bit since you've seen them, but it's a really important fact that we're going to be using. Do I have space here? I don't, but I'll erase it when we're done. So ignore what's on here for the moment, and I'll keep writing. So for right now, I've got the 1/2 still in front. Right now, I have the numerator, which we already had, was the 6t squared. Was it plus 18t plus 4? Okay, good. And we have the original denominator from the first piece, which was 3t squared minus 2 to the 1/2. And then we just discussed that we have 2t plus 3 to the 3/2 down here, right? And again, the reason that's happening is because as we take this piece to the denominator, I have a negative 1/2 exponent, and from right here, I have a positive 2 exponent. When I add those fractions together, I get 3/2. There's one more thing I can do to simplify. Does anybody see what it is? And it's not multiplying those denominators together. That is definitely not what I want to do.
Write a different way than denominator.
Before that, yeah. What do you have, Edgar? Yeah, there's a 2 right here, right? So if I recognize, all of this is in the denominator, so if I want, I could actually have this written sort of like this instead. I don't even need that 1 right there. That numerator has lots of things in it that are all divisible by 2, doesn't it? So since I can reduce all of them by the 2, I can simplify to not have the 2 there. So 6 divided by 2 is 3. 18 divided by 2 is, and 4 divided by 2 is 2. So the last thing that I end up having is 3t squared plus 9t plus 2 over 3t squared minus 2 to the 1/2 times 2t plus 3 to the 3/2. Now I want to come back to something that Edgar was noticing, that power 1/2 and that power 3/2, particularly if you were looking sort of in the back of the book at this particular one. What else might you see that written as? And what might they do instead of having powers of 1/2 and 3/2? They might have square roots involved instead, okay? I'm fine on this one with us leaving it with the powers of the 1/2 and the 3/2, but just referencing the back, if you're looking at an answer, recognize that that's the same thing, okay? Does that look good? All right. So this is what we have on this one. Okay. Problem number 4, which I'm about to erase my screen so we have space to work it, says that we're going to find the second derivative of the function. So now we've talked about what a second derivative is. What is a second derivative? Derivative of the first derivative. So it's the derivative of the derivative. All right, so taking a look at this one, the first thing that I would have to do is to take the first derivative, yeah. Now, looking at this, what do I need to do in order to actually be able to use all of these rules that I've been working with in order, for this particular function? Yeah, we make this with an exponent of 1/2, just like we did in the last problem, right? But this one's a lot prettier than the last one, isn't it? Looks simpler, at least for right now. We'll see. All right, so when I do my derivative, what am I going to get? Going to have a 1/2, good. And then I've got that set of parentheses. What's my new exponent going to be? Negative 1/2, fabulous. What's going to go inside? All right, x squared plus 4. Am I done? No, I need also what? Yeah, I need the derivative of the inside. What's the derivative of the inside on this one? 2x. Excellent. Now, again, on your test on Monday, quiz on Monday, we would stop right here, and I'm not going to ask for second derivatives anyway on the quiz. It's just going to be first derivatives. But in particular, this one shows you a very good reason why we want to simplify this, because if I'm going to keep going and taking another derivative, I want it as a clean, reduced, simple form as possible before I start making a bigger mess than I already have. Make sense? So what can I simplify with the expression that I currently have? There's not a ton, but there is a little bit. Right, this 1/2 and this 2, right? 1/2 times 2 is 1, so those would reduce to the value of 1. And then you have your choice of where you write these things, but I find it nicer to have the x written in front, so I'm just going to put the x at the beginning. And then the x squared plus 4 to the 1/2, negative 1/2, sorry, is at the end. If you choose to leave it the other way, it's not going to hurt anything. But that's the first derivative. You guys did it. But we were asked to find the second derivative. And what do you notice now with this function's first derivative, as I look towards taking the second derivative, that I didn't have before? It's already in the form we need. That's true. What else?
Like the X in front.
The X in front changes things. How? It's a product, isn't it? I need a product rule. Still have a chain rule. Still going to have that same chain rule that we did before. In fact, it's still the same chain, different power on the outside, but the inside's the same. But now I have a product rule too. So now I've got to do a product rule and a chain rule in the same time. Which one's going to happen first, the product or the chain? Can you tell?
Product.
The product, because I have a product of two different things, and one of the pieces product, one of the pieces that are being multiplied is a chain itself. Okay? So as I'm looking at this, I have one piece here, second piece here. That's a product rule. All right, product rule. How does that start? What do I do? First, I just write the first one down, right? Sure, that'll work. Then I have to take the derivative of the hard piece, or at least the harder piece. But you've done it already before, but you did it with power 1/2, and now we have a negative 1/2. But it's very similar. So what am I going to do to get the derivative of the chain? Okay, bring the negative 1/2 this time down, right?
Yeah.
And then I have this piece in the middle. To what power? Negative 3/2. What's going to go inside those parentheses? Just kidding, that's right. X squared plus 4 is going to go inside those parentheses, right? Don't be tempted to stop. It looks like we already did a lot, and we did, but we didn't finish it. All we've done so far is half of a product rule, right? The other half of the product rule says, what next? We'll need a plus sign, but then what next? Oh, I'm sorry. Yes, you're right. I was already getting carried away with the next part. What's missing there? Yeah, 2x. Thank you. All right, then my plus. Perfect. All right, so what comes next in my product rule? The derivative of the first. So what's the derivative of the first? That's 1. That's very nice. And then what do I do? Yep, I just rewrite the second one. X squared plus 4 to the negative 1/2. Now we're going to clean it up. There's kind of a mess going on, more of a mess than we had last time, right? So as I look towards cleaning this up, this one actually cleans up quite a bit. So it looks like a horrendous mess right now, and it's going to simplify down to a very nice, simple expression. So let's get going. What do you notice that you can simplify right away? Somebody tell me something. Yes, that's right. So Paula noticed that one before, didn't you? The 1/2 and the 2. That's a very nice simplification. I do still have a negative, as you mentioned, and I do still have the x at the beginning, and I have the x right here. So this one and this one. So x and x would be x squared, because these are all multiplied. So at the beginning, if you will, I actually have a negative x squared right now. And this piece right here is a negative 3/2. So what could I do to rewrite that in a more pleasing way? What did we do in the last problem? Do you remember? Yeah, we move it to the bottom. Exponents being positive is a much more common way of having the answer written. So we're going to move that to the bottom. It's also going to help us in a moment as we take a look at our denominators and comparing them. So this is actually the first expression, all sort of condensed down. Second piece right here, I don't really have a lot here to do except what?
Move that one to the bottom.
Right, move that part to the bottom. So I can write this one as the same part, is the part that's in parentheses is the same, but the exponent, of course, is different. You might be tempted to leave it like this. We're not going to leave it this way, and the reason we're not is because when we simplify this, it's going to be, when we combine these two fractions, it's going to become a whole lot simpler and much easier to work with as we do things with derivatives in Chapter 3. Right now we're just learning how to do them. We're going to be doing things with them in Chapter 3. So if I were to try to get a common denominator here, any idea what the common denominator might be? And this isn't just like, comparing 3 and 2 as a denominator and making a common denominator. This is more complicated, but any idea what it would be?
X squared plus 4 squared.
So obviously I'm going to have an x squared plus 4, right? How many of them am I going to have? What's the exponent going to be so that what am I going to have the exponent be to make them the same? I think I'm going to go with 3 halves. Is there none of the above that I could circle from you guys' choices? Watch this. This right now, 3 halves is the same as 1.5, right? And this is the same as 0.5, right? So if I were to take this second fraction and multiply by x squared plus 4, top and bottom, of course, this would have a power of 1, yes? So what happens when I have a power of 1/2 and I have a power of 1 in the same bases? I get 1.5, or 3 halves. So that's how I'm going to get these two to have the same denominator, is I'm going to multiply the numerator and the denominator by x squared plus 4. And I have successfully run out of room again, so we'll ignore the directions one more time as I move to the next screen. So we end up having the negative x squared we already had before, over the denominator x squared plus 4 to the 3 halves. And now I have x squared plus 4 in my numerator on the second fraction and x squared plus 4 to the 3 halves in the denominator. So what can I do? Yeah, I can combine the numerators now, right? Because they have the same denominator. So my new denominator is x squared plus 4 to the 3 halves. And what happens when I combine negative x squared, positive x squared, and positive 4? The x squareds cancel, leaving me with simply 4. Now, I told you it was going to simplify down a whole lot, didn't it? This is a lot easier to work with, actually computing things in Chapter 3 than what we had before. So that's why we've done what we did, is so that we'll be able to use this to find other things. Okay? Any questions on that one? Because I'm about to disappear it off the screen into Never Never Land. Okay, we have one more example. And then we're going to do something else today after that. You're not leaving early. We're going to have much more fun in math today. All right, last example, example number 5. This one tells us to compute the derivative, but what do you notice about the information you're given compared to the information we've been given in the previous problems? You're given some numbers in there. What are you not given? We're not actually given the function, are we? There is no f of x equals this, or g of x, or y equals, none of that's given. We're just given a lot of specific values, right? In particular, notice we're given, these are points. That's what some of you were saying at first, right? This is an xy ordered pair. That's what that is. What are these values over here? Those are slope values for my function that's my f function, my function f. And these are slope values for the function g, right? So let's take a look at how this works. This is the function we're given. We know that h of x equals f of g of x. And the very first thing we did today is that we actually wrote down a way of finding h prime of x. So what is the h prime of x formula actually look like? F prime of g of x. My pen is not writing smoothly today. Might be time for a new pen. Times g prime of x. Okay, this is exactly the chain rule, right? So that's what we're going to be working with. But that's not exactly what we were asked to find here. We aren't asked to find h prime of x. We're asked to find h prime of 1, right? So we're going to take this very same expression, but we're going to evaluate it at the point 1, or x equal to 1. Okay, so everywhere I had an x, I now have a 1. Now some of this already you know, because it was given to you. In particular, you now see g of 1 and g prime of 1, don't you? And those were pieces of information that you were actually given in the problem. What is, okay, the f prime, that's going to stay. We haven't dealt with him yet. He's just still there. What is g of 1?
2.
It is 2. And it says that right here. G of 1 equals to 2. And then, what is g prime of 1? Negative 2. And it says it on this piece right here, second line. So g prime of 1 is negative 2. Please do not be misled. This does not say f prime times 2, right? That's not what that says. Okay? And I make that mention because I don't want you to try to combine the 2 and the negative 2. That's not appropriate. This 2 right here, this negative 2 at the end, is multiplication, but it's multiplication times this whole thing right here. If it helps you to keep it in your mind a little bit clearer, you're welcome to put some brackets around it to sort of differentiate it, separate it from the other piece. Now, the good thing is you actually know what f prime of 2 is as well. It was also given to you. What is f prime of 2?
3.
That's 3. So the part that's in brackets, currently 3, is multiplied then by this number negative 2 to give me a grand total of negative 6. And it wasn't near as scary as you thought it might be looking at the directions, right? But you do have to go through it piece by piece. And you have to notice that all of the pieces of information they gave you at the front, we didn't use all of them, right? Okay, they're giving you more information than you need to make sure that you're understanding which pieces you do and when. That's what's going on. Any questions on this one? All right.